So, ladies and gentlemen, we are finishing the gas laws chapter today. And what we did last class, if I had to say the one topic that is the most important, I would say that that would be those problems where we combined gas laws and stoichiometry together into one problem. All right, so we're going to do a little bit more of that with a little additional component to it. And there's a lot going on in this picture here, but let me break this down into pieces. Okay, focus what's on the left here. We have a compound in a test tube, potassium chlorate. Okay, that doesn't even really matter. We're heating it with a Bunsen burner. We are decomposing this compound, and one of the products happens to be a gas. In this case, it's oxygen gas. And we need some kind of method, some procedure in order to collect that gas. And this is how it's done. All right, you've got a stopper in this test tube, so all of the gas that is produced is going to travel through this tube into this bowl of water, okay, and up into this upturned beaker, okay. Now, at the beginning of this reaction, this beaker would have been filled to the brim with water, okay, and I don't know if you can see this from where you're sitting, but these oxygen bubbles, okay, are going up and they're filling this space. And as the reaction goes on, the water level is going to drop and drop and drop as we collect more and more gas. Okay, well, great. What you're going to see in word problems is this phrase right here, that a gas was collected over water. And that is this procedure, okay? The gas is bubbled through water. And that's great. That's a nice, easy way to collect a gas. But there's a problem. If I tell you the pressure in this space here, and I'm just going to make up a number, and it's going to be a totally ridiculous number. If I say that the pressure in this space is 14 atmospheres. Now that's a completely ridiculous number, okay? That's like crushing pressure, but just go with me on it, okay? Total pressure in here is 14 atmospheres. Here's the problem. That is not the pressure of just oxygen. You may or may not be aware, okay, but anytime you have a sample of liquid, I mean, this is my water bottle here, in the space above that liquid, you will have some vapor particles from that liquid. So in this space, in my water bottle, sure, there's air up there, but there is also water vapor up there. Now, why does that matter? Why is that a problem? Because in this space is not just oxygen. There is water vapor in that space as well. Okay, so think partial pressures. That's the total pressure. If I give you the pressure of the water vapor, how could you get the pressure of just the oxygen, just O2? What could you do? Subtract. Okay, so let's say I tell you in the problem that the water vapor has a pressure of 3 atmospheres. Again, that's a ridiculous number. I'm just going for easy numbers here. If I subtract, then that gives me the pressure of just the oxygen, and that's what I want. Okay, is just the gas involved in the chemical reaction. Okay, but that is the phrase you want to look for. Right? So, let's jump to a problem. Okay, Okay, it says oxygen can be produced by the following reaction. This is actually the reaction that we were just looking at on that picture. Okay. What volume of oxygen collected over water? Okay, so I'm always annotating these problems. And there's that phrase we were just talking about. Total pressure of 94 torr, it's 22 degrees, can be produced from 2.6 grams of that guy. And then I give you the vapor pressure of water. Well, guys, this is exactly what I started class talking about. It's a gas loss situation, but we have a chemical reaction as well. So this is stoichiometry alongside that. Do you remember from last class, and go back and look at your notes if you need to, when you have this combined gas loss stoichiometry situation, what is the question you should ask yourself before you start the problem? Do you remember? Are my conditions at STP? Am I at STP? No. So let's come back to your answer. What must I use then? PV equals nRT. Okay, I'm just going to write it out because I know that I'll be using it at some point. Let's say it was at STP. What are you permitted to use if you are at STP? 22.4 as a conversion factor. But we're not. The way that I always start these problems, if I know I'm using the ideal gas law, I'm going to write it out. And like he said, I'm going to put check marks over my variables. What do I have? What am I missing? You guys take it from here. Check it. So let me just point something out. Okay, and I saw multiple people doing this as I was walking around. All right, you wrote this out, you started putting check marks, great. But what I saw was people said, oh, I'm missing moles, so let me take this number, KClO3, and convert that into moles, and then plug it in. Well, guys, what state of matter was KClO3? Solid. Can you plug moles of a solid into the ideal gas law? No, you can't. So, you have to go one more step to get to moles of the gas, and not just any gas, but the gas that we're concerned with. And then I have what I need to find the volume. The only reason I did this is because the gas was collected over water. Okay, so this whole collected over water business doesn't really change all that much. You just have to do a subtraction. But more importantly, what I want to call your attention to, because this is different than the problem we did last class. Okay, the gas loss stoichiometry class or problem we did last class, we used the ideal gas law first, and then we did some stoichiometry. And I told you it doesn't have to be in that order. And how do you know whether you can use the ideal gas law right away or not? I knew I couldn't because I had two unknowns. So you can't use an equation right away like that, okay? All right, so let's move on. Okay, guys, this kinetic molecular theory kind of wraps up this chapter, gives a little bit of description of what we talked about at the beginning of the chapter with what is an ideal gas. Okay, an ideal gas assumes that gas particles have zero volume, or very close. Okay, we know that particles do have volume. Now, is it a large volume? No, but they do. Okay, that's what differentiates a real gas from an ideal gas. Okay, we talked about pressure. come back to how did I ask you to visualize pressure? Do you remember? How do you visualize that? What does this mean? Right. Hits on the side of the container. If whatever you're doing is causing those particles to strike the side of the container more, that means the pressure must be going up. If whatever you're doing is causing fewer strikes, then the pressure must be going down. Okay? This is another characteristic of an ideal gas. Particles exert no forces on each other. So when two particles collide, which gas particles do a lot, it's saying no force. Physics people, if two things crash into each other, do they exhibit a force on one another? Yes, they do. Okay? But again, this is like the perfect gas. All right? And then one last piece, you may or may not be aware of this. I hope you learned this in Chem 1. This is a definition. The definition of the word temperature is the average kinetic energy. Guys, kinetic energy is the energy of what? Motion, movement. If you raise the temperature of anything, doesn't have to be a gas, all you're doing is causing the particles to move faster, have greater motion, greater movement. Okay, this is our last topic. And guys, I'm going to explain this to you with the world's most ridiculous analogy, but I promise you won't forget it. Okay? Diffusion and effusion. Okay? Let's start with diffusion. Focus on the second part here. Movement of one gas through another. Let me give you a real-world example. Okay? A couple of years ago, Oakton used to divvy up their locker assignments by grade. Okay? So for example, this hallway used to be the freshman hallway. Let me tell you how glad I was to have my classroom on the freshman hallway. Okay? But the way they used to do lockers is you got a different locker all 4 years so that you were on the sophomore hallway or the junior hallway. All right? So I lived on the freshman hallway for like 7 years. Anyway, here's a situation that came up a lot, and I'm going to throw the young men in this room under the bus because it was never a girl doing this. Okay, there is a wonderful product out there called Axe body spray. Okay, I'm sure it's a wonderful product when used in moderation. Okay, like one little spritz, that's all you need. All right, but no. Not even outside this door. It could be at the complete other end of the hallway. All right? There was always some kid, not one spritz. No. That is far too much. Okay? That is completely unnecessary. Okay? And so what would happen is, even if it's at the other end of the hallway, you'd have this cloud of Axe body spray, this gas that would diffuse down the hallway through this door over to my desk, okay, and I get real salty about it, okay, and then I'd come out into the hallway and fuss at this kid. But that is a perfect real-world example of one gas moving through other gases, okay? And are you ready for this most ridiculous analogy? Okay? It's ridiculous, you won't forget it. I want you to imagine this room is packed wall to wall, floor to ceiling with sumo wrestlers. I know, that's a really likely scenario, I know. Think of it as like a cocktail party for sumo wrestlers. All right? And they are body to body packed in here. Okay? You are at the back door of my classroom, and your objective is to get to the front door of my classroom. I want you to just picture that for a minute, all right? You are having to slither your way through these people, okay? Are you going to be able to do that quickly? No. All right, scenario number 2. This room is packed, wall to wall, floor to ceiling, with cute little bunny rabbits. Oh. It's still packed in here, but it's got bunny rabbits. You're at the back door, you need to get to the front door. Can you get there faster with the bunny rabbits?
No.
Yes.
Squish them.
So what if you're squishing them? Your objective is to move quickly, and you can. You know, moving aside a tower of bunnies is easier than moving a sumo wrestler aside. Okay? Well, let's bring it back to actual chemistry here. Okay? If you are the gas that is trying to move through other gases, the rate of diffusion is tied to molar mass of gases. Okay? Let's use our noble gases as an example. And I'm going to use extremes. If you have a room filled with helium, very small molar mass, versus a room filled with radon, hopefully not, it's poison. Okay? But large molar mass. A gas can diffuse through helium or radon faster. Helium, why? It has a smaller molar mass. Okay? So it's an inverse relationship. The smaller the molar mass, the greater the rate of diffusion. Okay, so helium is the bunny rabbits, radon is the sumo wrestlers. Okay, so that's diffusion. Let's talk effusion. Do you guys know, what's the prefix E or X? What does that mean? Out of, okay? We are talking about a gas escaping some small opening. Real world example, okay? If you have a balloon, you know how much I love balloons, or a balloon, those silvery ones that are made of mylar, or even an inflated beach ball. Anything inflated, if you let it sit for days, weeks, months, they deflate over time. Why? It's not like you're poking a hole in it. Why do they deflate over time? Well, what you may or may not know, doesn't matter what the material is, you know, rubber, latex, mylar, plastic, anything. Materials have these teeny tiny little holes. They're called micropores. Okay? They're not completely airtight, and the gas inside over time will escape. So that's a perfect real life application of effusion. All right, now let's come back to ridiculousness. All right, we're back at the cocktail party for sumo wrestlers. All right, they're body to body packed in here. Now you're not involved, or at least you're not in the room anymore. You are out in the hallway, and you pull the fire alarm. Which, by the way, people, if there is no fire and you pull the fire alarm, that is a federal offense. Not a misdemeanor, a federal offense, so don't do that. Anyway, you pull the fire alarm. The sumo wrestlers have to evacuate. Where are they going to evacuate? Through that door, as fast as they can. I want you just to look at the area of that door. I mean, how many sumo wrestlers can get out at a time? Like, maybe one? Maybe, I think that's being generous. Okay, maybe if we, like, grease the doorway and, like, shove them out, okay? But they cannot evacuate quickly. Right? Why? Because they're so large. Okay. Now we've got the bunny rabbits. All right. Now, obviously, bunny rabbits are not going to respond to a fire alarm. What do they care? They're bunnies. All right. So maybe we put a wolf in the back corner. All right. And the bunnies are like, hey, we got to get out of here. Okay, I don't want to be eaten. I don't want my face to be horribly disfigured by this wolf. Like, we got to get out of here. So the bunnies evacuate through that door. They can evacuate a whole lot faster. Anyway, so let's bring this back to chemistry. If I have a helium balloon versus a balloon filled with radon, which is stupid because radon is so heavy it would be a balloon sitting on the floor. Okay, but which balloon is going to deflate faster? Helium. Why? Smaller molar mass. You got it. It's the same relationship, inverse relationship. Okay? So diffusion and effusion, inverse relationship with molar mass. You may also have questions about like the velocity of gas particles. And here's an easy way to remember it. Fat people can't run fast. That's probably really insensitive. But honestly, fat people can't run fast. Large gas particles cannot move as quickly as smaller ones. So that, ladies and gentlemen, is the end of gas laws. But this chapter is on chemical equilibrium. So let's talk about what that even means. All right, so whether you know it or not, 99.999% of reactions are reversible. Now, what does that mean? That means you have reactants, you're creating products. These reactions can go the other way, where the products convert back into the original reactants. Okay? Most reactions can do that. Let me give you an example of one that probably wouldn't. Right? What is going to happen if you drop a match, a lit match, into the gas tank of your car? Not that you're going to do that, but what's going to happen? Kapow, right? Okay, and let's see if you remember this. You should. If you combust, meaning add O2, which is the same thing as lighting anything on fire, if you combust something primarily made of carbon and hydrogen, a hydrocarbon, what are your products? Do you know? CO2 and water. Okay? So your blown up car is mostly CO2 and water. Do you think you can somehow magically get the original car back? No. Okay? But the point is, most chemical reactions you can. Alright, so here's what happens. You start a reaction with reactants, right? Reactants only. And you start creating product, and creating product, and creating product, and creating product, and making more product, and product, and product, and product, and product. And eventually, your product pile starts to get too big, and the reaction starts to go in the reverse direction. Products becoming reactants. And when you have the speed of the forward direction is equal to the speed of the reverse, that is by definition chemical equilibrium. Okay, when the rates, the speeds in the forward and reverse are equal. Okay, we can look at this in a graphical way. Okay, let's start with the right-hand side. Look at what's on the y-axis. Rate, speed. And what you'll notice is the rate of the forward direction, reactants to products, which is how we start the reaction, immediately will start to slow down, whereas going the other way, products back to reactants, is going to speed up over time, but eventually they're going to reach the same speed, and that's where equilibrium has been achieved. Come over to this one, because this is a big misconception. Look what's on the y-axis. It's not speed, it's concentration. What's another word I could substitute in there? Molarity. Molarity. Okay, that's not the only form of concentration, but it's the most common. You'll notice that my amount of product, my concentration of product, increases at first. Okay. My amount or concentration of reactants decreases. Are they the same concentration at the end? No, they're not. but they are constant. And that is a big misconception. Put a star next to that statement. Equilibrium does not mean amounts or concentrations of reactants and products. It doesn't mean those are equal. However, they will stay constant. What's equal? That prefix, equal. What's equal are the rates, the speeds, not amounts. Okay, now, this is the first thing you're going to be asked to do in this chapter, and it is so simple. You will be given a chemical reaction. You'll need to make sure it's balanced, of course. And this is what you will be asked to do. Write the equilibrium constant expression. And ladies and gentlemen, this word expression means no numbers yet, no calculations yet. This is what an equilibrium constant expression looks like. This capital K here, and by the way, make sure you recognize that that is a capitalized K. Lowercase k means something else in chemistry. This is called the equilibrium constant. And if you're wondering why it's the letter K, because most of the scientists that did early research on equilibrium were German. The word constant in German starts with a K. Okay? When you discover things, you can name them whatever you want. Okay? If you discovered this, you could make this like, the symbol of a unicorn if you wanted to. I don't, whatever. What do brackets mean? Molarity, concentration, okay? Molarity of my products. Please notice they are being multiplied, not added, multiplied. Products divided by reactants. My coefficients become my exponents. And I'll show you in just a second what an example of what an expression looks like. I just want to call your attention to the fact that this equilibrium constant in this situation sometimes is written as just capital K. Sometimes you'll see it written as K with a subscript C. Anybody want to guess what C stands for? Doesn't stand for constant. What are these?
Concentration.
Concentrations. Yeah, exactly. It means an equilibrium expression written with concentrations. We'll see in a minute another way to write an expression. But here's an example, guys. Balanced equation. You're asked to write the equilibrium expression, and this is what it looks like. Final answer. Remember, expression means no numbers, no calculations yet. Okay? If this is a free response question, this might be part A. Part B might ask you to start plugging some numbers in. But guys, don't you see, if you had these molarities, plug them in and solve for K. Nice and easy. And you know what's even better news? You don't have to worry about units for K. Okay? K is usually expressed without units. How nice for you. Okay? All right, now, don't even read that yet. Just don't even read it. I know that's better, easier said than done. It's like passing a car crash and saying, don't look. Okay, I know. Here's what I want you to do. Move your eyes from this line right here down to this line right there. What happened from here to here? Yeah, the reaction's been flipped. Okay, well, maybe I give you the equilibrium constant value for this guy, and then the question says, what will be the equilibrium expression when it's written like that? Okay, well, let's think about this for a second. Anytime you have a K value or a K expression, what's in the numerator? I mean, what divided by what? Products over reactants. Okay. Well, I'm going to rewrite the number 10 to look more like a fraction. How about 10 over 1? If you flip this, what's the new K value going to be? 1 over 10, yeah. Okay, and you don't need a calculator for that. I could totally put this in multiple choice, because you don't need a calculator for that. So if you reverse an equilibrium reaction, and by the way, that's what these double arrows mean, something at equilibrium. If you reverse it, the new K value is the reciprocal. Okay? So that's one situation you can see. Let's look at another situation. Don't read that. Don't even read it. Move your eyes from here to there. What happened? Okay, all the coefficients were multiplied times 2. All right? Remind me, where do coefficients end up in an equilibrium expression? They're used as exponents. Okay? So I doubled all of the coefficients. My new K value is not going to be 10 times 2. You got it. It's the original K value raised to the power of whatever you multiplied by. Okay, so the new K value would be 100. What if you multiplied everything by 3? Exponent would be 3. You'd get what as your final K? 1,000. Okay. Now, if any of you are wondering, you know, why would you ever write a reaction like this when you can just simplify these coefficients? And we always say when you're writing a reaction, your coefficients should be as reduced as possible. So why would we ever do this? We haven't covered this yet. When we get to thermochemistry, there's a set of problems called Hess's Law problems, and they're actually really fun. Okay, it's all right. You don't have to admit to me that you think they're fun, but I know there are the silent people out there that think they're fun. There will be times when it's necessary to multiply the coefficients. Again, we'll figure that out when we get there. All right? So if you multiply your coefficients, you raise it to the power of whatever you multiplied by. Okay. Now, there's a lot going on in this table, but there's really, there's really one thing that I want, or two things actually I want you to get out of this. All right? Number one, an equilibrium constant can only change if you change the temperature, okay? And at the end of this chapter, or a little later on, we're going to talk about something called Le Chatelier's principle, which you did in Chem 1, and we'll see what raising or lowering the temperature, how does that affect this value? Because that's the only thing that can change it. This is sometimes the hard thing to get. And this chart is giving an illustration of what this is saying. It does not matter what molarity you start with your reactant or your products. The numbers do not matter. Whatever you start with, okay, is eventually going to settle out and reach equilibrium, and once it finally reaches equilibrium and we divide products by reactants, you will get the same K value, okay, or very close anyway. So what this is saying is, aside from changing the temperature, you can change the molarities all you want. But as soon as it settles out and the molarities adjust themselves, you'll always get the same equilibrium constant. It's okay to not believe me, but I swear it's true. Okay? So just a few slides ago, we saw Kc. What did the little subscript C stand for? Concentration. You can also write what's called a Kp expression. What do you think P stands for? Pressure. Okay. What state of matter do we talk about pressure? Gases. We don't talk about the pressure of solids, liquids. It's only gases. All right, so notice there's no brackets anymore. So we're not talking concentration. These are partial pressures. But the same thing applies. Products divided by reactants, your coefficients still become exponents. The thing to make a note of, you can, when you're writing a Kp expression, you only include gases. Kp expressions involve gases only. So, what if sulfur dioxide was not a gas? Now, it is a gas at room temperature, but let's just play pretend here. Let's say that's a liquid. Can you include a liquid in a Kp expression? Absolutely not. Don't you dare. So how is that going to affect my expression? That's just not there. Do I need to keep coloring here? Do you get the point? Okay, that's just not there. This would be my expression by itself. Let me make one other change. What if sulfur trioxide, not a gas, it's a solid, which it isn't, but that means I can't include that either. I'll change color here. So that's gone. What's in its place? 1. Thank you for not saying 0. That is my expression all along. Okay? So, the take-home message here is Kp expressions, gases only. What can you include in a Kc expression? Okay, well, let's look at that. I'll come back to that heterogeneous business in a second. Let's say this is my reaction. Here's my Kc expression. It looks kind of small, doesn't it? Like, where's the overreactance part? See if you guys remember this from Chem 1. What are the not one, two states of matter that you are permitted to include in a Kc expression? Clearly, you can include gases, not liquids, not solids, aqueous. All right? Kc expressions, let me be clear, meaning molarities, concentration, you are permitted to include gases and aqueous. You are excluding solids and liquids. Okay? Solids and liquids excluded. So let me just make sure that's clear. Kc expression, gases and aqueous. A Kp expression, gases only. Now, heterogeneous equilibria, okay? Think back to when we saw that word before, heterogeneous mixture. Or if that word is used in any context, a group of people is described as being very heterogeneous. What does that mean? What does hetero mean? Different. If your reaction has different states of matter, meaning they're not all the same state of matter, That's a heterogeneous equilibrium. If this was gas, 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 that would be a homogeneous equilibrium.